61A, Lecture 19, Q&A.
Hey, John, let me ask a question while we wait for somebody to chime in. When object-oriented first started, this notion of inheriting classes was very popular and I think was a big motivating factor. And you had this nice lecture at the end where you talked about how complicated it gets. Like what's the thinking these days with object-oriented? I've always found that once you get beyond one or two classes of inheritance, it just becomes unruly. Like where are things these days?
Good question. I think that there are definitely people who think that inheritance should be completely avoided.
Yeah,
But that's sort of an extremist view, I would say.
yeah.
A more common belief is that inheriting methods is fine.
Mm,
It's inheriting attributes that's
hmm.
complicated because, yeah, if you don't know where the attribute was originally declared, then it's hard to kind of keep track of what's
Yeah.
going on. So I see programs where, yeah, like functionality defined by a bunch of methods is inherited. Sometimes even multiple inheritance is allowed there. But you just
Yeah.
want to be careful about like having attributes defined in one place and then having a subclass that like tries to ignore some of those attributes because it's different enough that you don't want them all. That gets messy pretty fast, and it's usually better to just use composition instead.
Yeah, that sounds about right. I have to say, I think I'm much more likely to use composition than inheritance. That's really common.
Sure. So the question is about this complicated example and what's going on. And in particular, there was an example at the end about b.z.z.z, and why is that right, but four z's is wrong, and two z's is wrong, and one z is wrong. Once you have the right picture, then solving these problems is not so bad. So let's say that we had already gone through the work to draw a picture like this about what's going on. Then let's talk about how dot expressions are evaluated. This dot expression, b.z.z.z, is taking the dot z of something, but you don't know what it is until you compute it. And to compute it, you have to evaluate b.z.z. But you can't do that until you know what b.z is. You can't do that until you know what b is. B is just a name. So that's something we've been able to handle since the first week of class. We look in the global frame. We see that b is this thing. This object is a sketch of what it would look like to have an instance with a particular class. So this has the b class and a bunch of instance attributes. In this case, there's one called z and one called n. We're going to access the one called z, which brings us to this object. Happens to be another b instance. So this thing, one way to refer to it is b.z. How did I get there? I went to b, and then I went to its z. And I got to this object. Now, it also happens to have a z attribute. It's not like this is related to this one in any way. They just happen to have the same name, okay? So when you look at what's b's.z's.z, we have to follow this and figure out what we get, and then we get this object. So is the answer b.z.z an integer? No. b.z.z is an instance of the C class, so it's some object that's not an integer. But it happens to have an attribute whose name is z, and its value is 1. So if you evaluate b's z, 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 you get a number 1. So that's why which of these evaluates to an integer happens to be b.z.z.z as opposed to one of these other ones. If you were to take that integer and look for its .z, you would get an error. Integers don't have z attributes. And if you were to do either of these other ones, what you'd get back is one of these objects along the way. So b is an object, b.z is an object, b.zz is an object. It's only b.zzz that gives you a number. Okay, so sometimes there are these long chains, and we're just following them, basically looking at this from left to right. What's really going on is that we're figuring out what object to finally get the .z of, but to do that, we have to figure out what object to get this .z of, what object to get this .z of, and so you end up working from left to right in order to find the answer.
By the way, don't ever write code that looks like this, ever. This is a good pedagogical example, but this is not what your code should look like.
That is certainly true. Okay, so now let's back up a little bit and figure out how we got here in the first place. We started with this long example, And maybe we'll work our way up to a.z equals b.z by saying there's a class A, there's a class B, there's a class C, there's an instance of A, there's an instance of B, and then this doesn't create a new instance at all. This just is an attribute assignment. So this is changing the B object to have an attribute called n, which is value 5. This expression does create a new object, but I'm not sure that's the interesting one. So when you execute a class statement, you get a new class. When you execute this class statement, you get a new class. When you execute this class statement, you get a new class. So this has all happened before we actually made an instance of anything. When you make an instance that creates some object, now we're giving it a name using an assignment statement. So this is called A. And remember that when you create this thing, you have to execute its appropriate init method. It happens to be that the A class doesn't have an init method, so there's kind of nothing special about this object. It has no attributes at the moment. This one, on the other hand, when we create B, we're calling the B class. Oh, sorry, somebody needs to mute, I think.
Hold on, I'm going to start muting people.
When we call B, then we create an instance of the B class, but we do have to call its init method because it has one. And this is what always happens when you create a new object. You start it out as a blank slate, and then you start passing it in as well as any arguments to the original constructor. So y would be bound to 1, self would be bound to this B instance, and then we check if y is true, which it is. So we set self.z to something. And I put this ... because we actually don't really need to figure out what this does in order to answer the question of whether a.z equals b.z. Okay, so let's see what we can learn about this structure. If we look at A and try to find its .z, we first look at its instance attributes. It has none. So if we're looking for its z, we look next in its class. It's an instance of the A class, so we find that it does have a z. The z is the value -1. So that's what a.z would evaluate to. What about b.z? Sorry, b is this thing. When we look up .z for the b object, we look first at its instance attributes, and it has one. I didn't bother to figure out what it was yet, but I'm pretty sure it's not -1. So b.z will give you whatever this object is. If we finish the evaluation, we would have to go through and figure out what self.f returns. And we did that eventually in lecture. It returned this other B instance. So what this is evaluating is a.z, which is -1, equal to b.z, which is this B instance? And the answer is no. Like a number is never going to be equal to some object. Yeah, so let's sketch this out, and then we'll answer your question. The question is about if you're using composition instead of inheritance, how do you access the attributes of the elements of something? So if you have an account which has a balance, and we have a bank, which is not a subclass of account, it's just its own thing. And when we create a bank, we'll just have a set of accounts, which starts out as empty. And then we'll have like an open account. This is a little different than what was in the lecture, but it's pretty close. So what open account is going to do is it's going to create a new account with whatever name was passed into the bank. So the bank gets the name and uses the name to create an account. And now, how do we figure out how much money is in that account? This is sort of the minimal example. If I have a bank and I open an account for myself, I don't have a name for that account. I can't access it directly because it's not in the global frame. The only thing that's in the global frame is the bank, but the bank has a list of accounts. And there's now something in that list. So if I go into that list of accounts and get the element at index 0, whose account is that? That's John's account. And how much money is in it? $0, because we haven't deposited anything into it. So the answer in general to your question of like when you're using composition, how do you access attributes of the parts, is often using some like chain of dot expressions where instead of having a name for this account, you have an expression that's like some compound expression for this account that goes in and gets part of the Goldman with the bank, finds its list of accounts, gets its thing, and then gets its balance. Now, we could have had a method that does this instead. That would have been fine. But this is kind of the minimal example of how you would access some piece of the composed bank.
You can think about the account as just being, as John just said, one level removed from you. Instead of having a global variable that where you created the account, it's now stored in a list inside of another object. So now look at the command: object, Goldman, list, accounts, get the element, sub-0. What is that? That's now an object of type account. And now you can do whatever you want with it. You can access the member functions. You can access the data. It's as if we had just written John's account equals Goldman dot account sub-0. That's that object now. Now it's all the same thing. Yeah. So just levels of indirection you have to follow.
Yeah, good question. So the question is, can you use a syntax to refer to a method that just states which class contains that method, then the method name, and then call it where you explicitly pass in the object that you want to call it on? And the answer is yes. So if you have an account, there's really the normal way of depositing into it, which is that you would refer to the method by using a dot expression with the object that you're interested in. And you could think of this as shorthand for find the class of A and deposit into that using A as the account self and $12 as the amount. In fact, you could write this out if you really wanted to. Get the type A is an account and deposit into that $12. Now, you wouldn't write this because it's just like a more complicated version of this. It's allowed because this happens to be just a function, this function you've defined here. And so you can call it as a function. But there isn't really a good reason to do it. There happens to be, when you're using inheritance, occasionally a reason to reference things that you've overridden, and this is one way to do it. And so there's like an occasion where you would actually do this kind of thing. But it is allowed otherwise. It's just not something that I think is normally done.
Yeah, I think it would be considered poor form if you wrote that. I think you should avoid that because it's not something that most programmers would sort of do. And I mean, even though things are allowed, doesn't mean you should necessarily do them.
But it does illustrate, what is this doing? It's basically doing that. It's getting some function and filling in A. Yeah, good question. So what is super, which is some built-in function that really is quite magical, in my opinion, in terms of what it does. So it's better to describe what it does instead of how it does it. But what it does is it says, when you look up this method for, this is kind of related to self. Let's say self is a checking account. When you look up its withdraw method, skip the one that's in the checking account class and go find the one in the account class instead. We could have said this explicitly. We could have said, go find the one in the account class if we kind of knew where to look. This is asking Python to find it for you. It's saying, Python, about, what the parent, the superclass of, or base class of checking account is. So why don't you go find that version of withdraw? That's what this says. And this actually wasn't always the syntax in Python. There was like a different version of this in Python 2, I think. It works fine. People do use it. And it's a very subtle thing. It's basically saying, I want something that's just like self, except for it ignores the withdraw within the checking account and all goes and finds the one that was there before checking account was ever defined. Which, you could say that explicitly, go find the accounts withdraw, or you could have Python look it up for you.
Is it weird, John, that you don't have to pass self when you use the super notation?
Yeah, so that's an interesting thing, is that super isn't referring to the account class. It's like referring to a version of self as if account were its class instead of checking account were its class. So it's doing two things at once. It's going and finding the account class, and it's also filling in self for the withdraw method so that you don't have to pass it in explicitly. It is a lot to just like have a built-in function call with no arguments and somehow it does all that magic. That is what it is. So, you don't have to memorize this. We don't test you on it or anything like that. This one is a little bit more explicit, but it does mean that you have to be redundant. You have to say like, oh, the account is this base class, and that's the thing that I want to get the withdraw function from. Yeah, great question, and that's exactly right. So if there weren't a duplication or an overriding of withdraw where it existed in both checking account and the base class account, then you wouldn't need super. This is strictly a thing for when you have inheritance and you're using the same method name in both the subclass and the base class.
Although I would argue you probably should still do it as sort of a built-in documentation so that the user doesn't have to scroll through your class to figure out which one. It's sort of nice. The thing I like about making it explicit is you're telling somebody which one is it going to, as opposed to relying on some default. And then what if somebody actually comes in and puts a withdraw function later on? I mean, sometimes it's good to make things explicit, even if there's a default response,
Yeah. But one thing I would say is like if you have a deposit twice, which is like totally new, which is fine. Your subclass can have totally new stuff in it. And what you want to do is deposit this amount twice. You can just write self.deposit that amount and then do it again. You don't really need to use any supers here or anything like that. And you can trust that Python will look it up for you correctly. Yeah, good question. So the question was, in this example, if we made an A, but we passed in some argument when trying to construct an A, would you get an error? And the answer is yes. Since there's no in it, it's not expecting any arguments. So,
by the way, I've always thought this was weird that Python let you build a class without a constructor.
It is kind of a funny thing, but if we have no constructor, if it's just like no constructor here,
yeah.
Strangely enough, if you had an account that you managed to create successfully, while it doesn't have a balance, you could give it one later. So while this is possible, it's rarely terribly useful. The next question was, do you have to call init with the underscores, or could you call it something else?
You have to use the init. It's not a convention, because when you call the constructor, it has to know which function to call. And that's a special name, and it always has to be underscore, underscore, init, underscore, underscore. The
next question was whether you're supposed to know all of the special method names in Python, like underscore, underscore, init, underscore, underscore, and some other ones that we haven't covered yet, like underscore, underscore, stir, underscore, underscore. And the general answer is that we will cover this on Wednesday, tell you what you need to know and what you don't know, but here's our answer.
Well, you have to know the constructors, because you can't really build a class you can't build an object without them. And the str function is just what happens when you call print on an object. That's not fundamentally defined. And so you should know how those functions work but there's no, so yes, you absolutely should know how the constructor and the print functions work, or the str and the init functions, yeah?
So we'll go over the stir and repr functions in Wednesday's lecture, along with a couple of others. You don't have to know all of the special method names. There's like a long list of stuff that's built into Python, and we'll give you a kind of overview of what they all are in Wednesday's lecture, but you're not expected to memorize them all. But the ones that create string representations are particularly important, and as well as init. Okay, so the question was, why does this multiple inheritance version of an account give you only $19 when you deposit 20? Well, in fact, you've paid a $2 fee somewhere because there was $1 in there already. So depositing 20 should get you to 21, but instead it got you to 19 somehow. Why is that? Well, let's look back at the code. We came up with a savings account, which has a deposit fee of $2. And what happens when you deposit into your savings account is that you actually deposit the $20 minus 2. So we deposited $18, we had 1. That's how we got to 19. Why is it that this deposit got called instead of accounts deposit? Well, when you're finding which method to call, you look in the class first of the thing that you're depositing into. And if you don't find it there, then you look into its base classes. And then only after you've looked into its base classes do you look in the base class of the base class, which would find you the accounts deposit method, which doesn't do this nasty thing of taking out a deposit fee. So yeah, so basically you're finding methods here. Well, there kind of aren't any except for the init. Then here, and then the account class. And why the account class, even though it's not listed here? Well, that's because it's the base class of these. That's right. In general, in multiple inheritance, you look in both of these before you ever looked in the base class of one of these.
So think of it like a tree. There's the account class at the root. It has 2 subclasses, checking and savings. And then you have a subclass. You're just going to work your way back up the tree.
And if you're wondering whether it ever gets messy to figure out which thing happens first, the answer is definitely
yes.
In fact, like Python's now on its 3rd version of how to resolve this question, and because there were bugs in the first 2. So don't worry about it. This is beyond the scope of the course. But multiple inheritance does leave lots of computer scientists scratching their heads about what's exactly going to happen, which is why, in general, you should try to avoid it.
Yeah, I agree. I think one level of inheritance is more than I even care for, but I don't think you should be very careful when you go beyond that.
Yeah, so the question is this slide have anything to do with midterms? This did come from a past midterm. So we won't ask this kind of question because you could just run it and see what happens. I think this semester we're just going to focus more on getting things done rather than knowing exactly the mechanics. But exactly the mechanics of how the object system works as we've described it is part of the course, so you should know it. But I would guess there's more of a focus this semester on building things, implementing things, rather than tracing through a complicated example because of the online format. And that's fine for life as well, because getting things done is more important than understanding my very convoluted code. But there will be cases in which you find some complicated things out there in the world and you have to trace through them. So that is a useful skill to develop. Yeah, good question. So how do you keep track of what's an instance attribute and what's a class attribute and which one's which? I think instance attributes are just generally more common because usually when you're creating objects, you really want to focus on what's true about this particular object, and you just store that state as instance attributes. But it's not like class attributes don't show up once in a while, so you certainly have to know about them. This particular case where an instance attribute and a class attribute share a name does show up in practice, usually when you're trying to get something to do a different behavior than was originally intended. So you want to change the way this particular instance works so that it behaves differently than whoever wrote the class. And that, that is to be avoided when possible, but sometimes when you're building off of other people's code and you can't get them to change it, then you have to change it yourself by adding an instance attribute that's got the same name as their class attribute. So it's not like this never happens in practice, but it's the rarest of the 3 cases. So most common, everything's an instance attribute. Second most common, yeah, there's class attributes out there, but they have different names than the instance attributes. And then the third case is it is possible that you have a name collision and you should know what happens. Yeah, so the question is about this maximum subsequence question from lab 4, question 5. If you try to trace it, you get quite confused because there's just a lot of calls going on and how does it all fit together? So how else might you understand the implementation? Well, I'd say at the outset that it's often the case that tracing through tree recursion is not something that humans can tolerate. Like it's just really messy sometimes.
Gnarly.
So the right answer is to shift the way in which you approach understanding an implementation to get away from tracing and instead just treat the recursive calls as abstractions. They do the thing that they're supposed to do, but how they do them is not your problem. And then like you can put it together. But this is not like obvious or easy. So so maybe we could talk about that with a particular example. So maybe while I read this, maybe Hani can say
Yeah,
whether that makes sense to him.
I'll add one more thing to it. So John's absolutely right that tracing tree recursion is very hard because you have to hold a lot in your memory. So one way to fix it is, as he just said, is to just think differently about it. It's not about tracing. It's about thinking about the fundamental nature of the functions, and they just do what you want them to do. And the other is to just use toy examples. So if you have really small inputs, you can sometimes hold on to the recursion a little bit easier, as opposed to something like this that has, a ridiculous number of steps. So I do think that it does require a slightly different way of thinking as opposed to just drawing the environment map and mapping everything out line by line.
Yeah, that is actually great advice. Is like, think about maybe a 2 or 3 digit example if you want to trace it. Don't trace a 5-digit example for something that's going to do something with every digit. It's just going to get too messy. So how would this go? Return the maximum subsequence of a length at most t that can be found in the given number n. Well, if t is 0, then I think we only have one choice, which is to not take any of the digits of n at all. But then we have to decide, like, are we keeping the first digit of n? Or I guess the last digit of n is the easiest thing to access because we can access it like that. Are we keeping the last digit of n or not? So I think it's helpful to pick a value for n. So let's say n is 1, 2, 3, and t is 2, something like that. What would n% 10 give you? Just mark it up. Like this will give you 3. That part I think is worth tracing. And the rest, if we divide by 10, gives you 12. I think that, those pieces you should trace explicitly. Now what do? Well, you're either going to take 2 digits from 12, or you're going to take 1 digit from 12 and the 3 at the end. So that would be like keep the 3, but then you'd have 1 less digit for the rest of it, or you'd forget the 3 and you keep both the last digits. Now, you can think ahead. You can say, okay, well, what I should do is keep the 3 because it's big. But Python doesn't know that yet. So avoid the instinct of solving the problem for Python and instead just like let the computer work through the details itself. So you have the components. Now it's your job to say, well, I have 2 options. Option 1, let's say like keep last digit is option 1, which would mean that 3 is the last digit of this new number. How do you get it in there? You add it. But then this expression here needs to be all the other digits, and so it's got to have a 0 in its ones place. That's where that times 10 came from. And how do you get the rest of the digits? Well, that's where you make your recursive call. Get your maximum subsequence of the rest using t minus 1 because you already used up a digit, the last digit. And you don't need these parentheses. I was just trying to kind of guide things as we go. This, I think, you could trace in the following way. Instead of looking at the body of max subsequence, you should ask yourself, if I pass in 12 and 1 into here, what am I going to get? And you know the behavior of this thing. You know you're going to get 2. So 2 times 10 plus 3 is going to give you 23. That's the degree to which it makes sense to trace, is to pretend that this is some black box that does its thing, but you don't know how it does it. But you do know what its result is, which is like, what's the biggest digit in 12? Well, it's 2. And then the other option would be leave the, how about drop last digit, which means You're not going to use last. You're just going to use everything in rest, but you get to use t digits. And if you wanted to return the biggest one, then you just take the max of these two. When you're tracing through this, you want to say like, oh, what's this going to return? Well, this is 12 and this is 2, so this is going to return 12. And so what's this going to return? Well, the max of 12 and 23 is 23. So at least on this example, it seems like it's going to do the right thing. That's the kind of tracing that I would do in a tree recursive problem, and realize that we never went back through the body of max subsequence again. Instead, we just asked ourselves, what is this going to return, and stop there.
So there's that big leap of faith, right? Where you have to just trust that what you're doing is doing the right thing. And by the way, if you're wrong, well, then the code won't work. And so it like that. Hold on.
Oh,
I think there's another one. Yeah.
how about that? There we go. Sorry to cut you off there, honey. Yeah. So anyway, that's kind of the story. Is don't try to trace through the next call, because you're just going to get confused. If you wanted to let Python draw the environment diagram for you so you can watch it happen, that would be fine. But doing it by hand is really, really tough.